Richard Feynman, one of the greatest physicists of the 20th century, once said something that should trouble you. He said, "I think I can safely say that nobody understands quantum mechanics." Now, Feynman wasn't being modest. He wasn't making a joke. He was stating what he believed to be a simple fact. Quantum mechanics, the most successful theory in the history of physics, the theory that underlies everything from the device you're using to watch this video to the nuclear reactions in the sun, is not understood. Not by Feynman, not by Einstein, not by Bohr or Heisenberg or Schrödinger, not by anyone. And here we are, nearly 100 years after the theory was formulated, and the situation hasn't changed. Physicists still don't agree on what quantum mechanics means. They don't agree on what it says about reality. They don't agree on how to interpret the mathematics that they use every single day. This is, on the face of it, an extraordinary situation. Imagine if chemists couldn't agree on whether atoms exist. Imagine if biologists couldn't agree on whether evolution happens. That's roughly the situation in quantum mechanics. The calculations work, the predictions are confirmed, but nobody knows what the theory is actually telling us about the world. Some physicists find this embarrassing. Carroll, a prominent theoretical physicist and author, has written that physicists should be outraged by this state of affairs. He thinks we do understand quantum mechanics, or at least we could understand it if we just accepted the right interpretation. For Carroll, that interpretation is many worlds. The idea that every quantum event causes the universe to split into multiple branches, each containing a different outcome. I have great respect for Carroll. He's a brilliant physicist and a gifted communicator. But I'm not sure he's right. I'm not sure anyone is right. And I want to explain why the disagreement persists, why it might be deeper than it appears, and why the honest answer to the question, "What does quantum mechanics mean?" might simply be, "We don't know." Let me start with the problem that has haunted quantum mechanics since its birth in the 1920s. It's called the measurement problem, and it goes like this. In quantum mechanics, particles don't have definite properties until they're measured. An electron doesn't have a definite position. It has a wave function, a mathematical object that assigns probabilities to different possible positions. Before you measure it, the electron is, in some sense, in all those positions at once. It's in a superposition. This isn't just a statement about our ignorance. It's not that the electron has a definite position and we just don't know what it is. The theory says, quite explicitly, that the electron doesn't have a definite position. The superposition is the reality. But then you make a measurement. You look to see where the electron is. And suddenly, instantaneously, the superposition vanishes. The wave function collapses. The electron is now in one definite position. You see a dot on your detector, not a smear. This is deeply strange. Before the measurement, the electron was spread out, existing in multiple places simultaneously. After the measurement, it's localized, existing in one place. What happened? What caused the change? What counts as a measurement? The standard textbook answer, often called the Copenhagen interpretation, is essentially, don't ask. The measurement is a primitive concept. When a quantum system interacts with a classical measuring device, the wave function collapses. That's the rule. Apply it and move on. But this is unsatisfying for obvious reasons. What makes a measuring device special? A measuring device is made of atoms. Atoms obey quantum mechanics. So why doesn't the measuring device go into a superposition along with the particle it's measuring? Where exactly is the boundary between the quantum world and the classical world? And why should there be such a boundary at all? Niels Bohr, one of the founders of quantum mechanics, insisted that there must be a classical realm, a realm of definite properties where measurements happen and results are recorded. But he couldn't say where this realm begins. The boundary is arbitrary, movable. You can push it further and further back, including more and more of the apparatus in the quantum description, and the theory still works. But eventually you have to stop somewhere. Eventually something has to be classical. Why? This is the measurement problem. And despite nearly 100 years of effort, it has not been solved. Not definitively. Not to everyone's satisfaction. Now there are proposed solutions, many of them, and they're called interpretations of quantum mechanics. Let me walk you through the main ones. The first is the Copenhagen interpretation, which I've already mentioned. Copenhagen isn't really a single interpretation, but a family of related views. associated with Bohr, Heisenberg, and their colleagues. The core idea is that quantum mechanics is a tool for predicting the results of measurements, and that's all it is. The wave function doesn't describe reality itself. It describes our knowledge of reality or the probabilities we should assign to different outcomes. On this view, asking what the electron is doing when we're not measuring it is meaningless. The question has no answer. Quantum mechanics doesn't tell us about an observer-independent reality. It tells us about the relationship between preparations and measurements. Everything else is metaphysics. This might sound like a cop-out, and in some ways it is. But it has a certain austere honesty to it. Bohr was deeply skeptical of the idea that physics could give us a God's-eye view of reality. He thought our concepts like position and momentum were tied to measurement contexts and couldn't be abstracted away from them. Quantum mechanics for Bohr was teaching us the limits of what we can know and say. The Copenhagen interpretation dominated physics for decades. It's what most physicists learn in school. It's what most physicists use in practice. Shut up and calculate is the slogan sometimes attributed to Feynman, though he probably never said exactly that. The point is, do the math, make predictions, collect your Nobel Prize, and don't worry about what it all means. But not everyone was satisfied. Einstein famously never accepted the Copenhagen interpretation. He thought quantum mechanics was incomplete, that there must be some deeper reality beneath the probabilities. God does not play dice, he said, though Bohr reportedly replied, "Stop telling God what to do." The most radical alternative to Copenhagen is the many worlds interpretation, proposed by Hugh Everett III in 1957. Everett was a graduate student at Princeton, and he had a simple but audacious idea. What if the wave function never collapses? In the standard story, when you measure an electron that's in a superposition of being here and there, the wave function collapses and you see one result. But Everett said, what if the wave function doesn't collapse? What if it just keeps evolving according to the Schrödinger equation, which is perfectly deterministic and never involves any collapse? If that's what happens, then after the measurement, the wave function describes a superposition not just of the electron but of you. There's a version of you that saw the electron here, and a version of you that saw the electron there. And these two versions no longer interact. They've decohered. They're effectively in separate worlds. This is the many worlds interpretation. Every quantum event causes the universe to branch into multiple copies, each containing a different outcome. All outcomes happen. There's no collapse, no measurement problem, no special role for observers. The wave function is all there is, and it describes a vast, constantly branching multiverse. Sean Carroll thinks this is obviously the right interpretation. He argues that many worlds is the simplest, most elegant, most parsimonious formulation of quantum mechanics. It takes the mathematics seriously and doesn't add extra postulates. The wave function evolves. That's it. Everything else follows. And there's something to this argument. Many worlds does have a certain elegance. It removes the mysterious collapse. It treats measurement as just another physical interaction. It unifies the quantum and classical realms by saying everything is quantum, always. But I have reservations, and I want to be honest about them. The first reservation is about simplicity. Carroll says many worlds is the simplest interpretation because it adds nothing to the basic quantum formalism. No collapse postulate, no hidden variables, no special role for observers, just the wave function and its evolution. But is that really simpler? Many worlds postulates an infinite number of unobservable parallel universes. Every time a quantum measurement happens anywhere in the universe, new branches are created. The number of branches is unimaginably vast and growing every instant. Now, Carroll would say that the branches aren't additional postulates. They're consequences of taking the wave function seriously. The wave function already contains them, so the theory is simple, even if its implications are extravagant. I understand this argument, but I'm not entirely convinced by it. Simplicity in physics isn't just about the number of postulates. It's also about the kind of entities a theory commits us to. A theory that says there's one universe with some strange measurement dynamic seems intuitively simpler than a theory that says there are infinitely many universes constantly splitting off from each other. This is a judgment call, of course. Different people weight simplicity differently, but I don't think it's obvious that many worlds wins on parsimony. It might just be trading one kind of complexity for another. The second reservation is about probability. In quantum mechanics, outcomes have probabilities. If an electron has a 70% chance of being here and a 30% chance of being there, and you do the experiment many times, you'll find it here about 70% of the time. But in many worlds, all outcomes happen. Both branches exist. So what does it mean to say that one outcome has a higher probability than another? This is called the probability problem, and it's been a thorn in the side of many worlds since Everett first proposed it. Various solutions have been attempted. Some involve counting branches. Some involve decision-theoretic arguments about how a rational agent should bet. Some involve new axioms about how to assign measures to branches. Carroll and his colleagues have worked hard on this problem, and they believe they've solved it. They argue that the Born rule, the rule that tells you how to calculate probabilities from the wave function, can be derived from reasonable assumptions about rational behavior in a branching universe. I'm not sure the problem is solved. Many philosophers and physicists remain skeptical. The derivations involve assumptions that some find question-begging, and there's something deeply strange about a theory where all outcomes happen but some are more probable than others. I'm not saying the problem is unsolvable. I'm saying it's not obviously solved, and that should give us pause before declaring many worlds the winner. The third reservation is about what we might call the incredulous stare. This is a phrase philosophers use for a reaction that's not quite an argument, but is still meaningful. When you hear a philosophical thesis and your immediate reaction is, "That can't possibly be right," that's the incredulous stare. Many worlds invites the incredulous stare. It says that right now, as you read this, there are countless versions of you in parallel branches of reality, living different lives, making different choices, reading different sentences. Every quantum event that has ever happened has split you into multiple copies. The you reading this is just one branch among unimaginably many. I know that the incredulous stare isn't a rigorous objection. Our intuitions evolved to deal with medium-sized objects moving at slow speeds. They're not reliable guides to fundamental physics. Quantum mechanics is counterintuitive no matter how you interpret it. But still, the incredulous stare points to something. It suggests that many worlds, whatever its theoretical virtues, is making a claim about reality that is extraordinarily extravagant. And extraordinary claims require extraordinary evidence. What's the evidence for many worlds? There isn't any direct evidence. There can't be by the theory's own lights. The branches don't interact once they've decohered. You can't send a signal to your counterpart in another branch. You can't detect the other worlds. Many worlds is compatible with all the evidence. But so is Copenhagen. So is pilot wave theory. So is QBism. The interpretations make the same predictions for all experiments we can actually do. They differ only in what they say about unobservable aspects of reality. This is why some physicists and philosophers think the interpretation question isn't really a scientific question at all. It's a metaphysical question, a question about what we want our theories to mean, not a question that experiments can settle. Let me briefly mention some other interpretations, because many worlds isn't the only alternative to Copenhagen. There's pilot wave theory, also called de Broglie-Bohm theory. This interpretation says that particles do have definite positions, always. The wave function doesn't describe the particle itself, but a pilot wave that guides the particle's motion. The wave function never collapses because it was never the whole story in the first place. Pilot wave theory is deterministic. Given the initial positions of all the particles and the initial wave function, the future is completely determined. The randomness of quantum mechanics arises only because we don't know the initial positions precisely. Einstein would have liked pilot wave theory. It restores the kind of realism he valued. The world has a definite state whether we measure it or not. But the theory has costs too. It requires a kind of non-locality that some find disturbing, and it treats position as special, which seems arbitrary. Why position rather than momentum or some other property? Then there's QBism, which stands for quantum Bayesianism, though its proponents now prefer to just call it QBism. This interpretation says that the wave function represents an agent's personal beliefs about what will happen if they make a measurement. It's not about the world, it's about you. On this view, quantum mechanics is a user's manual for navigating an uncertain world, not a description of objective reality. Different agents can have different wave functions for the same system, and that's fine. The wave function is in the head, not in the world. QBism is radical. It seems to give up on the idea that physics describes an observer-independent reality. Critics say it's solipsism dressed up in fancy mathematics, but its proponents argue that it dissolves the measurement problem by refusing to ask what the world is like apart from our interactions with it. There are other interpretations too. Collapse theories like GRW, which modify the Schrödinger equation to include spontaneous collapses. Relational quantum mechanics, which says that quantum states are always relative to an observer. Consistent histories, modal interpretations. The list goes on. Here's what I want you to notice. Each of these interpretations has strengths and weaknesses. Each solves some problems and creates others. Each has brilliant advocates who find the other interpretations obviously wrong, and they all make the same predictions. They're all empirically equivalent, at least for any experiment we can currently imagine doing. You can't test which interpretation is correct by doing more physics. This is why the debate has gone on for nearly a century. It's not because physicists are stupid or lazy. It's because the question is genuinely hard. It might be a different kind of question than physicists are used to answering. In most of physics, you propose a theory, derive predictions, do experiments, and check if the predictions match. If they do, the theory is confirmed. If they don't, it's refuted. That's the scientific method. But the interpretations of quantum mechanics all make the same predictions. The scientific method, as usually understood, can't distinguish between them. So what method should we use? Some people say, choose the simplest interpretation by Occam's razor. But as I've argued, different people assess simplicity differently. Carroll thinks many worlds is simplest. Others think Copenhagen is simplest because it doesn't postulate unobservable entities. Others think pilot wave is simplest because it restores determinism and realism. Some people say, choose the interpretation that best fits with the rest of physics, especially relativity and future theories of quantum gravity. This is a reasonable criterion, but it's not decisive. Many worlds proponents argue their interpretation plays best with quantum gravity. Pilot wave proponents have developed relativistic versions of their theory. The jury is still out. Some people say the question is meaningless. If the interpretations make the same predictions, they're just different ways of talking about the same thing. There's no fact of the matter about which one is true. I have some sympathy for this view, but I don't fully accept it. The interpretations say very different things about the nature of reality. Either there are many worlds, or there aren't. Either particles have definite positions, or they don't. Either the wave function is objective or subjective. These seem like different claims about the world. Not just different ways of talking, but if they're different claims about the world and we can't test them, what do? Here's my honest answer. I don't know. I've spent decades thinking about quantum mechanics. I've worked on quantum field theory, quantum information, black hole physics. I use quantum mechanics every day, and I cannot tell you which interpretation is correct. What I can tell you is that I'm suspicious of anyone who claims certainty on this question. When Carroll says that many worlds is obviously right and other interpretations are obviously wrong, I think he's overstating his case. When Copenhagen loyalists say we should just shut up and calculate, I think they're avoiding a real question. When QBists say the wave function is just in our heads, I think they're giving up too easily on objective reality. The honest position, it seems to me, is humility. We don't know what quantum mechanics is telling us about the world. We have several interesting proposals, each with virtues and vices. We should keep working on the problem. Keep trying to find experiments that might distinguish between interpretations. Keep refining our philosophical analyses. But we shouldn't pretend the problem is solved when it isn't. Feynman was right. Nobody understands quantum mechanics. Not in the sense of having a clear, agreed-upon picture of what it says about reality. But here's the thing. That's okay. It's okay because science doesn't require that we understand everything. Science requires that we make progress. And we have made enormous progress. Quantum mechanics works. It predicts the outcomes of experiments with extraordinary accuracy. It has enabled technologies that have transformed human life. Whatever quantum mechanics means, it has been spectacularly successful as a scientific theory. The interpretive questions are important. They matter for our understanding of the world. for our sense of what kind of universe we live in. But they don't stop us from doing physics. They don't stop us from applying quantum mechanics to new problems, developing quantum computers, exploring quantum gravity. It's also okay because intellectual humility is a virtue. The universe is not obligated to be comprehensible to human beings. Our brains evolved to track predators and find food on the African savanna, not to understand the nature of reality at the deepest level. It would be remarkable if we could understand everything. It's not surprising that some things remain mysterious. I find this thought comforting rather than distressing. The universe is stranger and more wonderful than we can fully comprehend. Quantum mechanics gives us a glimpse of that strangeness. We can marvel at it even if we can't fully explain it. And who knows? Maybe someday someone will find an experiment that distinguishes between interpretations. Maybe someday a new interpretation will be proposed that makes everyone say, "Of course, that's obviously right." Maybe the problem will be solved. But even if it isn't, even if the measurement problem remains a mystery for another 100 years, that's okay too. Some questions are worth asking even if we can't answer them. Some mysteries are worth contemplating even if we can't resolve them. Let me end with a thought about what quantum mechanics might be teaching us. Every interpretation of quantum mechanics in its own way challenges our ordinary assumptions about reality. Copenhagen challenges the assumption that the world has a definite state independent of observation. Many worlds challenges the assumption that there's only one world. Pilot wave theory challenges the assumption of locality. QBism challenges the assumption that physics describes an objective reality at all. Maybe quantum mechanics is trying to tell us that our ordinary assumptions are wrong, that reality is not what we think it is, that our intuitive categories, position, momentum, state, observation, break down at the fundamental level. If that's right, then our confusion about quantum mechanics isn't a failure. It's a sign that we're bumping up against the limits of our conceptual framework. The confusion is the message. Bohr seemed to think something like this. He thought quantum mechanics was revealing the limits of human description, the point at which our concepts fail to track reality. He wasn't upset about this. He thought it was profound. I think there's something to this view, though I'm not sure Bohr got the details right. Quantum mechanics is pointing to something deep about the nature of reality, something that doesn't fit our ordinary ways of thinking. The disagreement about interpretations reflects genuine uncertainty about what that something is. And that uncertainty, that disagreement, that ongoing puzzle, that's not a scandal. That's science. Science is not a collection of finished truths. It's an ongoing process of inquiry, of testing and questioning and revising. Some questions get answered, others remain open. The open questions are often the most interesting ones. Quantum mechanics has been one of the most fruitful theories in the history of science. It has also been one of the most puzzling. Both things are true. The puzzle doesn't diminish the achievement. If anything, it makes it more remarkable. We have a theory that predicts reality to extraordinary precision, and we don't know what it means. That's strange. That's wonderful. That's physics. So what should you think about quantum mechanics? I'd say, embrace the uncertainty. Learn the formalism. Marvel at the predictions. Explore the interpretations. But don't let anyone tell you that the question is settled when it isn't. Don't let anyone tell you that one interpretation is obviously right and the others are obviously wrong. The measurement problem is real. The interpretive disagreements are real. The mystery is real. And that's okay. In fact, that's more than okay. That's what makes it interesting. A universe that we fully understood would be a universe with nothing left to discover. The fact that quantum mechanics still puzzles us, nearly a century after it was formulated, means there's still something to learn. Feynman said nobody understands quantum mechanics. He was right. But he kept working on it anyway. He kept asking questions, proposing ideas, pushing forward. That's what scientists do. That's what we should all do. The mystery isn't a reason to give up. It's a reason to keep going. The wave function evolves. The particle appears, the measurement happens, and somewhere in the mathematics there's a reality we haven't fully grasped. Maybe we never will. Maybe that's the point. The universe is not obligated to make sense to us, but we can keep trying to understand it anyway. That's the human project. That's physics. That's enough.